When writing the answers to multiple choice questions, examiners try to think of the mistakes that pupils are likely to make. By working through this series of 6 videos, you'll be made aware of those mistakes and you'll be in a better position to avoid them when sitting your National 5 Physics exam. Let's get going with the first space physics question then. The weight of a robot on Earth is 240 newtons. The weight of the robot on Mars is... So first thing to remember is that an object's mass is constant, although its weight will change depending on the gravitational field strength where it's situated. On Earth, gravitational field strength is 9.8 newtons per kilogram, and on Mars it's 3.7 newtons per kilogram. Both values are found in the datasheet at the front of the exam paper. That means the robot's weight on Mars will be lower than that on Earth, so we can rule out 2 of the options. After that, we can calculate the robot's mass using this equation. If we then substitute the robot's weight on Earth and the gravitational field strength on Earth, then we get this. Dividing both sides by 9.8 gives us mass m is equal to 240 divided by 9.8, which is 24.5 kilograms. The robot's mass will also be 24.5 kilograms on Mars, so we can use the same equation again, but using the gravitational field strength on Mars. That gives us 24.5 times 3.7, which is 90.65 newtons. Written to 2 significant figures, that's 91 newtons. And the answer of C. Next up, another question involving Earth and Mars. A rocket accelerates vertically upwards from the surface of the Earth. An identical rocket accelerates vertically upwards from the surface of Mars. The engine thrust from each rocket is the same. Which row in the table shows how the weight of the rocket and the unbalanced force acting on the rocket compares on Mars and Earth? So it'll help to remind ourselves that the gravitational field strength on Earth is 9.8 newtons per kilogram, and on Mars it's 3.7 newtons per kilogram. It might also help to bring in a rocket to help visualise the problem. The 2 vertical forces acting on the rocket at takeoff are the thrust acting upwards, which is the same for both rockets, and the weight force which acts downwards. Since the gravitational field strength is smaller on Mars, the rocket on Mars will also have a lower weight. Because of this, the unbalanced force, that's the difference between the thrust and weight, will be greater on Mars. That means our answer must be D. The next question is all about light years, which is of course a unit of distance. The distance from the Sun to Proxima Centauri is 4.3 light years. This distance is equivalent to... The first thing I'll do is explain how to calculate 1 light year. We use the equation d is equal to vt. Distance equals speed times time. Since a light year is the distance travelled by light in 1 year, the speed we use is the speed of light, 3.0 times 10 to the power of 8 metres per second, which we can find in the datasheet at the front of the exam paper. For time, we have to work out the number of seconds in a year, so we multiply by 365, the number of days in a year, then 24, the number of hours in a day, then by 60, the number of minutes in an hour, and finally by 60 again, the number of seconds in a minute. That gives us 9.15 times 10 to the power of 15 metres for 1 light year. For the number of days in a year, we could have used 365.25, but it won't actually change the final answer. To calculate 4.3 light years, we just multiply 9.15 times 10 to the power of 15 times 4.3, giving an answer of 4.1 times 10 to the power of 16 metres, which is E. The next question looks as if you'll need to do a calculation, but it's actually all about interpreting the information given and spotting a pattern. The communication satellite Iridium 124 has a period of 97 minutes and an orbital height of 630 kilometres. The geostationary satellite Astra 5B has a period of 1,440 minutes and an orbital height of 36,000 kilometres. A satellite with an orbital height of 23,000 kilometres has a period of... Now, I'm not suggesting you waste your time in an exam drawing up a table of orbital height and period, so I'll do it for you, using the data given in the question. It's clear to see then that there's a pattern. As orbital height increases, period increases. This is something you should know anyway. The height of 23,000 kilometres fits in between these 2 values, so it follows that the period of a satellite at that height must be between 97 and 1,440. The only possible option is C. Up next, it's a question about starlight. Light from stars can be split into line spectra of different colours, The line spectra from 3 stars, X, Y and Z are shown, along with the line spectra of the elements helium and hydrogen. Hydrogen and helium are both present in, then we have the answers, which we'll put over here. First off, if helium is present in the stars, then all 5 of the lines in helium spectra will be in the spectra of the star. Let's take a look. Here's the first. Then the second. The third. The fourth. And finally, the fifth. To summarise, all 5 lines are present in the spectra of stars X, Y and Z. Let's take a look at those 2 lines in the spectra of hydrogen. Again, if hydrogen is present in the stars, then both of the lines in hydrogen spectra will be in the spectra of the star. So, this is the first line. And this is the second. If we look closely then, we can see that hydrogen is present in stars X and Z, but not in star Y. That means our answer is D. So, it looks like we've dropped the other 4 options, just like you could drop a like on this video. While you're at it, why not subscribe to the channel so that you're made aware when new videos are released. Keep watching and good luck in your studies.